Hello all. Before I get into what we're doing in this video, let me apologize for my background, which is a little more chaotic than I normally like it to be. My office is currently under renovation and hopefully will be fixed soon, but in the meantime, I'm going to make these videos anyway. All right, our topic for this set of videos is a brief overview of machine learning. I'm going to give you a lot of information in a very compact form. You can take a whole class on machine learning and spend a lot more time on each of these ideas. We're just going to kind of dive in and take a look at a lot of things, and then we will focus on a small number of actual machine learning models that we'll work with more closely. All right, I'm going to switch over to show you my notes and we'll get started. So the topics for today, I want to start by thinking about machine learning and its place within artificial intelligence because it's been very successful lately. It gets talked about a lot. A lot of people assume that AI is machine learning, and it is an important component of the field, especially right now. But there are also things we want to think about it from an AI perspective that might differ than the ways that a data scientist or a statistician might think about machine learning. So I want to be pointing some of those out to you. We are going to also talk about generally different categories of machine learning, different kinds of ways you can do machine learning, and we'll dig into the supervised learning task. That's what we're going to spend most of our time on because that's, I think, by far the largest segment if you look across all different kinds of machine learning that happen. And then we're going to spend some time talking about how we evaluate machine learning models because that's a critical component. You can't just build a model and then step back and say, yeah, that's great. You have to actually know how well it works in order to be able to tell if it's working the way that you want it to, and to be able to assess whether there's more work to do in trying to improve it. So we'll talk about loss and accuracy. We'll talk about different kinds of metrics that get used for doing this analysis, and we'll talk about some visualization methods, such as like a confusion matrix. And we'll also talk about a method, cross-fold validation, which is used as a way to better validate the performance of a model. All right, so we're going to start with this question because this is artificial intelligence, and part of what we want to do is to pay attention to how the the methods that we're looking at relate to what humans or animals do. That's not everyone's goal in machine learning, but it's an important goal within the field of artificial intelligence. So from the outside, when you just see a machine learning algorithm doing what it does, especially like the very interactive ones like generative AI and chatbots that exist right now, from the outside they seem very impressive, and there's a common theme, which is once you start to learn how they work and how they're trained, sometimes that shifts you from being super impressed all the way to the other extreme where you feel somewhat disappointed. That they're not doing what we impute to them. Learning is a very loaded word. It means something very deep when we talk about humans or even animals. And what machine learning algorithms do is depending on who you are, it will not match very closely what you imagine is happening when people are learning. So we can sometimes end up disappointed and concerned that this is not learning in any real sense. It's also, though, very successful, right? So we can train a robot to walk using machine learning by having it explore with trial and error until it figures out what's going to work for it. We can have AI agents that learn to play video games. We have chatbots that learn through interactions with humans to imitate them. Or they're also trained on documents and data and interactions, dialogues that humans have with each other, and they learn to imitate those. And they're very impressive. So we're at this point where there's some things that look really impressive, and the methods underlying them may or may not match what people do. So there's a lot of research yet to do in terms of understanding human learning And at the same time, then we can compare it to machine learning. So very, very often with machine learning models, the learning is limited to one task. You know, the agent that learns to play Mario Kart is not able to do anything else, not even play Super Mario, without a total change. Now, we think of a lot of chatbots as being exceptions to this because they're trained on text and increasingly in multimodal forms where they can operate on text and audio and images and maybe video. So there are these different pieces that go into them, which makes their learning seem less limited. But fundamentally, they are around replicating human conversation, if it's a chatbot, human discussions. And generative AI systems that say generate images or video, that's typically what they're trained to do. They're trained to take some text and produce an image that matches. And they couldn't say, sit down and play chess. And there's certainly many kinds of problems that AI chatbots can't solve. They're no good at it, and some of those are things that we humans are particularly good at. So we know that it's not capturing some aspects of human learning. All right, so if you think about machine learning as its own task, this is typically how people in data science or software engineering oftentimes, they apply machine learning as an algorithm for building models of data. You've got data, you build a model, you can explore that model to understand the data better, or you have a practical application where you just want to crank some data through a machine learning algorithm, get a model and use it. So there isn't a lot of like AI agent there. It's almost just another tool. It's just another algorithm, and there's nothing particularly special happening. Data goes in one end, and what comes out the other end, sometimes it's called an artifact or a model. AI people will sometimes refer to these things as a hypothesis. But fundamentally, model, I think, is becoming the standard term. It's a representation of the things that the model has determined, or that the algorithm has determined. And typically, almost all machine learning algorithms are statistical pattern finders in one way or another. Because they look for patterns in different ways, they have different strengths. So a particular data set, you might find that one algorithm, machine learning algorithm, works really well and another doesn't, but you switch to a new data set and maybe that situation will flip-flop. Because of the nature of the kinds of patterns that each different algorithm is good at finding, they have their places where they're going to succeed and places where they will not succeed as well. But fundamentally, when you think about machine learning, it's all about finding patterns in data and then being able to generalize from the patterns that are found. It's not thinking about whether a pattern is appropriate or reasonable. It's not reasoning about what are the necessary and sufficient conditions for categorizing something as, say, a chair. It's just finding patterns among all the chairs it's seen, and then using that pattern to infer that an object might be a chair. It's possible that you could decide that that's all that's going on in our own brains, but I don't think that's all that we have going on in our brains. And so there's a point at which machine learning and human learning are still very divergent from each other. All right, so as we're thinking about AI agents, how do we incorporate machine learning? What does this look like? So machine learning for an AI agent is a tool for improving the performance of the agent. We have an agent that wants to perform a task. Machine learning can form a part of it so that it can perform the task better. The result of the algorithm is then sort of inserted into our agent as part of its decision making. So we still have this idea of an agent in an environment. It gets some inputs and it makes a decision and it takes some actions. It's just that now maybe there's a machine learning model that's helping to inform the decision that it's making, as opposed to hard-coded things that a programmer has written. So almost any component of an AI agent could be set up as a learning process. So I'll use my own research over many years. I've looked at a number of different machine learning tools and tasks for machine learning. So in my own research, I have small robots. They navigate the science building full of hallways and classrooms and labs and open spaces. And I have variously applied different machine learning methods for a number of different tasks. So starting at the very bottom-most level of the AI agent, you think of it as a reflex agent that's trying to move around without hitting things, running into walls. So I've used machine learning to help it to learn how to adjust its speed and movement parameters based on the environment that it's in. So in crowded environments, maybe it slows down, maybe it allows itself to get closer to obstacles, whereas in a big open space, it can move more quickly and it can also stay further away from obstacles and therefore be safer. So I have had projects where that's what we were exploring, was how well does that work? And my current machine learning task is learning how to map camera images to locations. So that's a completely different task. It's high level, it's localization, where the robot needs to know where it is, and it uses its camera image to try to deduce where it is. I've also used machine learning to determine whether an area seems safe to pass through. So the robot has a map, it knows what an area should look like, getting some feedback from its sensors about how crowded the area is, and maybe what it needs to do is learn that a certain level of crowd is not a good idea, and it should just not try to go that way. So all of these different aspects of this simple robot system could be handled with machine learning, and possibly even different machine learning systems. In my case, they have been very different pieces. Another aspect that we think about when we think about this from an AI perspective is this question of whether the learning is online or offline. Offline learning is probably 90% of what happens in machine learning. So offline learning means that the learning is taking place not while the agent is active and engaged in its task, but before it starts its task or in between episodes of its task. So with offline learning, when we're creating this AI agent, we go out and collect a big data set. We run a machine learning algorithm until we get good behavior, and then we take that model and we stick it into our AI agent and we set it loose to do its task. And that new AI agent, it's not learning anymore. It's not learning on the fly. It learned offline, and now it's just putting that into practice. This is the most common approach. Most of the learning that chatbots have done has been offline. They have a little bit of online learning that has been incorporated into at least some of the chatbots so that they can stay current, so that they can personalize to you as a user. But fundamentally, the bulk of the learning has been done offline. Online learning is harder and also very, very interesting from an AI perspective, because this is how we and animals learn. We learn while we are doing things. We don't sit down and have somebody download learning into our heads. We learn through doing, through being in the world. We are online and we learn. So therefore, this is closer to what humans learn, how humans learn, and therefore it's something that we're very interested in. So the agent learns from its experiences actively all the time. So if you have reinforcement learning, this is what falls into online learning. So if you had an agent like my robot and I wanted it to do online learning, then what would happen is it would be recording its experiences, evaluating them perhaps, and then changing its behavior. So the next time it's at that particular location, it will hopefully do better than it did before. There are lots of different forms of online learning. Reinforcement learning is the most common, and it's a very interesting area of research. One of the interesting parts of it is that there is a certain amount of evidence that forgetting is a key component of online learning. You don't want to remember everything. You want to forget some things and maybe remember patterns instead of the whole. All right, so as AI people, why do we use machine learning? Well, we want to learn about learning. So we want to build artificial systems that somehow model one aspect or another of learning. That's where machine learning started from. And then because these tools are so successful at certain tasks, that kind of has taken on a life of its own. We also are really interested in making systems that can adapt to changes in their environments. So, we talked about that categorization of different kinds of environments. We all imagine an AI agent moving toward a situation where it exists in the real world. In robotics, you've got it in the real world. But even with other kinds of agents we might imagine, we think about them as moving into more dynamic, more elaborate environments, and that's an interesting step of progression. That requires that the system be able to adapt to its environment. We can't possibly pre-program everything that an agent might need to know about living in the world. We can't just hard code it all, so it has to learn it somehow. There also are a lot of situations, and this is probably the biggest reason that we use machine learning, is that we don't know how to solve the problem. And so we see, well, maybe machine learning can solve it for you. So for instance, in my research, if I could figure out a really, really simple pattern that I could hard code for my robots to detect where they are in the world, I would do that rather than going to machine learning. But I've been unsuccessful at extracting information from images otherwise than using machine learning, and so therefore I use it. And I have an example here. This was many years ago. I saw a presentation at a conference by someone, I believe it was GE, General Electric, so don't quote me on that. There was also a guy there from like Ford Auto and a couple of other corporations, so I could have this wrong, but yes, I believe this is General Electric. One of the products that General Electric at that time produced were painted plastic beads. Not really painted, but plastic beads with color infused in them that could then go to a company and be melted down and formulated into plastic parts that had specific colors. And this is where the auto company comes in, I think. One of the big purchasers were car companies. They want to be able to have painted panels and plastic bumpers that match in color. And so they have very specific needs for the colors that they want these plastic bumpers to have. General Electric at that time had a unit that would produce beads of specific colors. So the trick was that this had grown over time. And at the particular moment in time when I saw this at a conference, they were facing a problem, which was that they had a lot of really expert designers who worked in their office, and their job was to take in a new order and a description of the color that was needed and pick out base colors that could be blended to make that color. That process was not that hard to replicate. What was hard to replicate was that these older workers were really good at picking out base colors, like the minimal set of base colors that would actually produce the color that was desired. And that saved a lot of money. And the problem they were facing was that the workers were not very good at articulating how they made those decisions. So they had people sit down with them and they would say, how do you do this? How do you decide what base colors to use for this color? And they'd be like, I don't know, it just kind of reminded me of these other ones we did, and it just seemed like these were the right colors. So they had all this knowledge, but they could not articulate it, which meant they couldn't teach new people how to do it. So all of these older workers, they're nearing retirement. The new younger people are not anywhere near as skilled. And the company was looking for an alternative. And so they turned to machine learning. They had filing cabinets full of all their old color recipes that told what the color was and how to make it with base colors. And they'd pull them out and reuse them as needed. So they trained a machine learning algorithm on all of those old recipes. And it was darn near as good as the older workers once it was done, and way better than the younger workers. Now, this is also a cautionary tale. One of the issues with AI in general is that these AI systems displace workers. What did the company do? Well, they just moved those younger workers to somewhere else, or they got rid of them, they fired them, and now there are not nearly as many people working in that office. It's just people who run the program that does the color design automatically. So yes, AI always has this issue. So does really any technology that we work with. There's always this problem that what we're doing can displace people. And it's something we should all think about. All right. But generally speaking, this is an example of the kind of problem that people would go and want to apply machine learning to within the AI community. A problem that exists that we just couldn't solve with other methods. And so machine learning seemed like a good option. If you've got data and otherwise you can't come up with a simple algorithm to do the task, then you might as well see if machine learning can find patterns in that data. All right, the next thing I have here is a whole list of terminology. Not all of these are critical that you actually, I don't want you to memorize these. Part of what this notes document is for is that you can go back to it and just look them up and see what the various pieces of terminology are. But these are things that we're going to talk about, so I thought I'd include some of them here. A term that AI people use is induction or inductive reasoning, as opposed to deductive reasoning. So deductive reasoning, you go from evidence to a outcome, to a result. With inductive reasoning, you take a set of examples and you generate a general rule for them. So induction is what machine learning systems are doing in that sense. Prior knowledge, those are the things that an agent knows before learning starts at all. There may be prior knowledge or there may not be prior knowledge. We've talked before about like our state space search where we've embedded knowledge in the actual system. You could still have that with an AI agent, and then it could be using machine learning as well. Prior knowledge also might be an understanding of different ways of encoding data. So for instance, when we deal with text, we often re-encode sentences using a vector representation of the words, for instance. Training from scratch. That means that our machine learning model does not have any knowledge of the problem given to it, and we're training it just based on the data. And that's the most common situation for machine learning. Factored or vector representation. We take the data that we have and we want to represent it as a vector, an array, and where each cell in the array is some attribute, and that attribute has a value of some type. Now, the data could be numbers, integers, floating point. It could be text. It could be other things. You can have representations that include images, sound, and so forth, but those typically require special handling. You can't just take an image and turn it into a vector and have it work well unless it's a very, very, very small image. All right, then I have a couple of tasks here. These are sort of two big tasks. We'll talk more about these in a little bit. Classification is the most common machine learning task. So you're given input examples and your goal is to categorize them. So maybe I put in pictures, and each picture is a picture of either a cat or a dog or a horse. And my goal for the model is that it's able to predict whether or not it's a cat or a dog or a horse. That's classification in a nutshell. Regression is also a very important piece of machine learning. We're not going to spend that much time on it because I believe our statisticians do a really good job of focusing on the regression side of things. But basically you have input examples and the output is intended to be a number. So the model is in some way approximating a function of some kind. So if you need to output numbers, then you use regression models versus classification is some ways a simpler task. Transfer learning is a key idea. This is going to come up over and over again, so I thought I'd include it here. So using a model that has already been trained by someone else for some other task, and then using it for your task. The transfer learning also implies a certain way of using that, but there are variations on this. It sometimes is also called retraining, and it's also called fine-tuning. Those are variations. They don't all mean exactly the same thing, and as we go further, we'll get into those a little better. But this is a common tool these days, especially with large scale models. You may not be able to, you may not have access to computing resources or data to fully train a great big model, one of our deep learning models. So you can always start with something that was already trained by someone else and then try to adapt it for your purpose. There are lots of other tasks, there's lots of other terminology I could go into, but we're going to stop there. We will come back in the next video and we will talk about different kinds of machine learning a little bit more in detail, supervised and unsupervised and reinforcement and so forth. And then we'll have another video or two that go into the details of evaluating models and also looking at some examples using a common library in Python. So I will stop for now and I'll see you very soon.